average both ends of the interval. Each one of them will have a weight of 1/2 compared to the other ones. Whereas, so that's for the linear approximation. For the constant approximation, everything has a weight of 1, and you have one less point. And just that makes a huge difference. So it's very small difference in the actual procedure that's being executed, but which means that it's kind of surprising that you would get a true benefit from just this pretty minimal thing. But in actuality, it does pay off, because mathematically, we can understand the strange difference in performance of these two algorithms if we look at the math. But you could also ask, well, are there other methods like that which just look at a certain number of points and assign relative weights to each of these points? And are there other methods like that which are better than either one of these two? I mean, we know some specific methods that are better. For example, the method that assumes that it's a polynomial of degree 2. This method as well is going to boil down to just a this method as well is going to boil down to just having points on a grid and assigning a certain weight to each of those. And yet it's going to vastly outperform the linear approximation. One other thing that you can notice, so sometimes the actual accuracy that you measure is not the accuracy you expected. Usually when that happens, the accuracy you expected was really good and the accuracy you got was really bad. And that often indicates that there is a small bug in the program. So for many programs that you write outside of computational physics, if you have a bug, it's rare that the answer is basically right, but just less precise. It's a rare. Usually, you have a bug and something really bad happens, or there's just something that's noticeably not working. But in other circumstances, there's this phenomenon that you can basically screw up the code, but you still get a valid algorithm. It's just a less performant algorithm that you thought it would be. And the opposite is true as well. Like if you look long enough for by trying many different things, it's possible that you find an algorithm that's actually much better than you thought it would be. Because in a sense, we do understand these things in terms of this mathematics of Taylor expansion. But on the other hand, everything in this kind of integration, this polynomial integration, boils down to having a sweep, a for loop like that, and different weights for different places. And so if you didn't know about the analytical underpinnings of that, then the behavior of these algorithms would be pretty mysterious, because you would just need to find the right weights, and then you have a really good performance. So we'll come back to that, but there's actually a way to take this idea to say, okay, I'll play with the weights, and I'll also play maybe with where I choose the points, on how I make my grid at which I evaluate this function, in such a way as to maximize the precision. And in this case, it turns out that we can do it. We can get pretty far with just this idea that we're going to maximize the accuracy by choosing these weights. Okay, so that's that. Another thing that we saw was root finding. And we saw that you could simply find a root by finding an interval on which inside of which there's only one root. By root I mean, x is a value of x where f of x gives you 0. You can find a root by picking an interval that there's only one root inside, and then also that both boundaries for the interval are of opposite sign, so that the function just goes through the 0 point at only one place. And then you do this bisection method. Bisection means like cutting by 2, cutting by a factor of 2. And you do that long enough, you get with a small interval. But there's another way to find the root of a function, and it's to assume that the function has a certain form. For instance, to assume that the function is linear. It's just to sort of give you a narrative, to follow between integration and root finding. The truth is that you have all of these methods that you sometimes use. They're not necessarily related. There are many ways of arriving at these methods that have nothing in common, but just so that it's easier to follow, there's this kind of trick that you can, or this theme that you say, okay, well, I'm going to suppose that the thing I'm working with, which is completely general, actually isn't that general. I'm going to get a method, and then that method might be approximately correct for general functions. But how do you know? How do you know that it's not completely inaccurate, so that's completely useless for some functions? Well, you don't know usually, because it's a hard question to answer. And usually the answer is that it's not robust 100%. That being said, when you have several methods that are not robust and you know in which way they're not robust, you can sometimes combine them or find methods in between which actually have the right robustness characteristics that you're looking for. So let's find the roots. Let's find the root of this function. Find root is a pretty descriptive name. So double x So just to be clear, epsilon will be the error. So the basic idea is that imagine that f of x is equal, or f of y is equal to some constant times y plus some other constant. Right? What's the zero of that function? Well, you say f of y equals to 0. That gives you you put b on the other side, you get minus b equals m times y, and you put m on the denominator, so you get minus b over m equals to y. Alright, so if you knew the slope of the function and you also knew the constant factor, and you knew you could find the zero of the function. So it's worth looking into, but in our case we'll know the function, so we'll know f0 and x0. Alright, so if you have a slope f of x minus f0 is equal to the slope times x minus x0. That's the same as saying that the slope is the change in the function when you change the variable, right? So we need to find